Alright, so in this section we're going to talk about logarithmic functions. So the one thing that you really need to just remember is that logarithms are actually just the inverse of exponentials. Alright, so in other words, you can see here if we let a be a positive number, so that means a is greater than 0 with a is not equal to 1, then the logarithmic function with base a denoted by log base a is defined by log base a of x equals y, and this is an if. This symbol here means if and only if, meaning if one side of this is true, the other side is also true. So if and only if. All right, so they both have to be true here. Log base a of x equals y, if and only if a to the y equals x. So last week I actually used b instead of a, but it doesn't really matter here what you call the letter for the base. But here in both of the cases, though, what you need to notice is that the a is the base, and then the y is the exponent, and then the x is what the value is equal to. And so this x value is what I usually call the argument. So if I look here and I have log base a of x equals y, this is the base, this is the argument of whatever the log is equal to, of what what this is equal to, and then this is going to be the exponent that the base is raised to get this value of the argument. All right, so the common logarithm is the logarithm with base 10, and actually let me turn this light on. For some reason I thought it was on, and then I noticed some shadows there, so hopefully this is a little bit better. But the logarithm with base 10 is called the common logarithm and is denoted by omitting the base. So if you see a log written without a base there, then that means it is just base 10. So this just means that the base is equal to 10. So in other words, what I'm saying is that if you called this actually some letter like y because you don't know what it is, then that would be the same as 10 to the y power equal whatever that x would be. That's the argument of the log. All right, so here are some examples of changing the logarithmic form to the exponential form. So you can see that in the first one, log base 10 of 100,000 is 5, so that means 10 to the 5th power is equal to 100,000. So you can see that that's exactly what happened for all of these, that the base was the same for the logarithmic and the exponential form, but then these were all of the exponents. So these are just different ways, essentially, of writing the same thing. All right, so again, if you have any questions, feel free to just let me know. But right now, I hope that you can see all we're doing right now is just rewriting the forms back and forth between logarithmic form and exponential form. So if I want to convert each exponential form equation to logarithmic form, then in this particular case, I see that the base is equal to 1/5, and the exponent is equal to -5. So it would be log base 1/5 of the argument 32 is equal to -5. Similarly, for the next one, the base is 1/3, and that's raised to the -3 power, so the exponent is -3, and so this would be rewritten as log base 1/3 of this 27 here is equal to the exponent of -3. So again, it's just a different way to write this equation here. So now this next example, example 2, is going to be converting the logarithmic form to an equivalent exponential form. So here we have log base 1/2 of 1/8 is equal to 3. So the base is 1/2 and the exponent is 3, so we have 1/2 to the 3rd power. And then even if you didn't know anything about logarithms, you should still be able to figure out that 1/2 to the 3rd power is 1/8. So if the statement that you're writing down doesn't make sense, then you know that you've written it down incorrectly. All right, so this should be a true statement that 1/3 to the, what is it? Yeah, 1/2 to the 3rd power is equal to 1/8. So the next one, log base 1/5 of 1 equals 0. So the base is 1/5 and the exponent is 0. So I have 1/5 to the 0 power is equal to 1. And again, even if I knew nothing about logarithms, I should be able to know that the 1/5 to the 0 power is equal to 1. So again, if there's any questions, feel free to just put them in the chat. But right now, again, I'm just transferring the notation back and forth here. All right, so now if I want to evaluate each logarithm, then remember that each logarithm is going to have 3 parts to it. Log base a of x equals y. So a base, an argument, and an exponent. All right, so I am going to evaluate this logarithm by just saying, well, and by the way, this is a set of problems where when I'm asking evaluate each logarithm, I mean logarithms where the exponent is missing and you have to figure out what the missing exponent is. So we have 3 to the x, the missing exponent will be 81. So 3 to what power is equal to the 81? Well, if I think about it, I can rewrite 81 as 3 to the 4th power, and so then x is equal to 4. All right, so again, 81 is 9 times 9, and each of those 9s is 3 times 3, so 81 is 3 to the 4th power, so that means x is 4. All right, if I want to evaluate log base 2 of 1/8, here the exponent is missing again, so I'll just call it x. So I have 2 to the x is equal to 1 over 8. And then I can rewrite that 1 over 8 as 1 over 2 to the 3rd, or 2 to the -3 power, so x is -3. So in both of these cases, I figured out what the value of the logarithm was. Here, log base 3 of 81 was 4, and here log base 2 of 1/8 is equal to -3. All right, let's try another one. Solve each logarithmic equation for x. So in these problems, I see that the this one at least, the argument is missing. So if the argument is missing, again, that's an easier problem because I can just write it in the base to the exponent form. So 3 to the 4th power is x, and 3 to the 4th was 81. So x is 81. But in this problem, the base is missing. So I have log base x of 5 is equal to 2. So I have x to the 2nd power is 5. And then I just take the square root on each side. So if I take the square root of x squared is equal to plus or minus the square root of 5. So x is equal to plus or minus the square root of 5. But if you remember, the base must be greater than 0. So since the the base x has to be greater than 0, that means x has to be the square root of 5. All right, so there you go. X is the square root of 5. So usually we don't deal with bases that are not whole numbers, but you can have that, like in this case. Just remember that the base has to be positive and not equal to 1. All right, let's try another one here. And again, if you have any questions, please just feel free to ask. But in this problem here, log base 3 of 8 is equal to x. The 3 is the base. The x is the exponent. So I have 3 to the x is equal to 8. And, well, this one is a little bit more difficult to answer because I don't actually have a way to write that 8 as actually 3 to a power, right? But I can tell you though that since 3 to the 0 is 1 and 3 to the 1 is 3 and 3 to the second is 9, I can tell you that the answer is going to be between 1 and 2. All right, so if I had to give you an estimate of the answer, I would say that it's between 1 and 2. All right, so I do know for sure x is between 1 and 2, but if I wanted to get an exact answer, this is where I think I would definitely need a calculator. And one way to do this would be if your calculator has logs with different bases on it, then you would just go ahead and do that. Like, where is it? Oh, number 5 here. So log base 3 of 8 would be 1.89, and I can see that probably makes sense because the 8 is closer to the 9 than it is to the 3. But I will say though that x then would be about 1.892789261. But if I didn't have a calculator that could do log with different bases, then I could use what's called the change of base formula. And by the way, the reason why I showed you this over here is because say any problems where you wouldn't be allowed to use a calculator, then I would just maybe expect that the question would ask you to give an estimate of what the exponent might be in between. In this case, it was 1 and 2. But if you had a calculator that didn't have the ability to put in a base, then you can use the change of base formula. So if you have log base, say, b of x, that's log base, in any other base, like a of x over log base a of b. So the b is the argument for the denominator and the x is the argument for the numerator. So you don't have to let a be any specific number, but if you let it be 10, then you could say that this is a log base 10 of 8 over log base 10 of 3. And again, remember that if we just have a base 10, we don't even need to write the 10 because it's assumed to be 10 or the common logarithm. So that's log 8 over log 3. And most calculators have a log button that won't necessarily calculate any base except for 10. So if you have log 8 over log 3, you get the same result. All right, so that's how you would do this in a basic scientific calculator rather than maybe a fancier graphing calculator. All right, so the next one here, a log of x equals 0.2413. So here the base is missing. So the base is 10, the argument is x, and the exponent is 0.2415. So I can rewrite this as 10 to the 0.2415 is equal to x. And this is not one that I'm going to do in my calculator without needing to, mix the decimals together with the exponents here. Like it's kind of strange having that decimal in the exponent, but it's possible for that to happen. So x should be about 1.743813357. All right. So again, that should make sense because 10 to the 0 power was 1, and 10 to the first power was 10. So 10 to the 0.2415 power should be somewhere between 1 and 10. All right, so it was 1.7438133357, about that amount right there. All right, the next one, log of 3x minus 2 is equal to negative 0.7. So here the base is not given again, so base is 10, and the argument is 3x minus 2, and the exponent is negative 0.7. So I have 10 to the negative 0.7 is equal to 3x minus 2. And then try not to do any rounding until the end. And if you do, then make sure that you still write out every digit your calculator gives you. So you could do 0.199526231 is equal to 3x minus 2, and then add the 2. So 2.199526231. Again, this is approximation because you went ahead and you did the decimal early, but that's okay as long as you write out every digit until the final answer. So that's 3x, and then if I divide by 3, I get x is approximately 0.7331754,105. All right, there you go. So the next one here, we have log base 6 of 6 to the 5th power, and this one, the exponent is missing, so we don't know what the exponent is. The exponent is missing, so I'm going to rewrite this as the base of 6 to the missing exponent is 6 to the 5th power, and so therefore x will just be 5. All right, so there you go. So that's a quick little introduction into converting between the exponential and the logarithmic forms. So now here, let me move on to graphing these logarithmic functions here. So the inverse of the exponential function y equals b to the x is y is log base b of x. All right, so these are inverses. So some properties of this logarithmic function: domain is 0 to infinity, range is negative infinity to infinity, the function is 1 to 1, the b to the power of log base b of x is equal to x, the graph passes through the points 1, 0 and b1, the y-axis or line x equals 0 is an asymptote of the graph, and if b is not stated, it's equal to 10. And another case is when b is equal to e. So we'll talk about that in a little while, but you can't really see that very well. But log base 10 of x is just log 10. But if we have log base e of x, that's ln oh, sorry, 10 log base 10 of x. So I wouldn't rewrite log base 10 of x with the 10 in it again. I would just say log x and ln x like this. All right, so that's a little e there, but I can barely see it myself. So just remember that these are two special things, or two special cases where the base might not be written. It's the common logarithm base 10 and the natural logarithm base e. And then the graph follows the usual properties of vertical and horizontal translation. So we'll graph the logarithmic functions by just its properties and then using vertical and horizontal translations after that. So now let's try to find the domain of each of the following functions. So f of x is log base 10 of 2x minus 1. So just remember that this just remember that the problem here said that the domain was 0 to infinity, right? So since the domain is 0 to infinity, what that means is that this part, this 2x minus 1 has to be greater than 0. All right, so just try to remember that since the domain of log base b of x had to be greater than x greater than 0, then whatever you do when you shift or translate the graph in any way has to still maintain that property that this argument is greater than 0. So then I'll go ahead and I'll add the 1 and I'll divide by 2. So I'll get x is greater than a half. So the domain for this one, log base 10 of 2x minus 1 is 1/2 to infinity. All right, so now let's graph each function by using its exponential form and determine the domain and the range here. So another way to write y is log base 4 of x is 4 to the y power equals x. So that's what I mean by graph this using its exponential form. So in this case, if I make a table of x and y, remember that x was 4 to the y power. So usually I would substitute values for x and get a y value. But here I want to substitute values for y and get an x value. So if y is 0, 4 to 0 is 1. So there's a point at 1, 0. And if y is 1, I have 4 to the 1 is 4. So that is going to be 4, 1. And remember I said that 1, 0 and b1 were points on the logarithmic function's graph. And so in this case, the base, was actually equal to 4. So this makes sense that this would be the points 1, 0 and 4, 1 on the graph. Now, remember that there is an asymptote at, here, let me show you again. All right, at x equals 0. So x equals 0 is an asymptote. So here it is, x equals 0. And so x equals 0 is the vertical asymptote, and then there's a point at 1, 0 and at 4, 1, and then if you kept on going, it would be at well, 4 squared is 16, so 16, 2. So it's way out here somewhere. So I already know that the graph will look like this. All right, and remember to make sure that you draw the graph approaching the vertical asymptote but not crossing it. So here was the point, here it was 1, 0, and here's the point 4, 1, and the domain would be, well, 0 to infinity, and the range is all real numbers, negative infinity to infinity, because any y value could be substituted in here. All right, I hope that you're enjoying this here. So let's try another one here. So we have f of x is equal to log base a third of x. So y is log base a third of x. So base is equal to b is equal to a third. So another way to write this is a third to the power of y is equal to x. So if I make a little table here, that means that x is 1/3 to the y. So I'll pick values for y again, like 0. So 1/3 to the 0 is 1. If I pick 1, I have 1/3 to the 1 is 1/3. 2, 1/3 squared is 1/9. And so I see what's going on. So I might actually want to pick negative numbers like -1. If y is -1, then I get a positive, right, a positive 3. If y is -2, I get a positive 9, and that might be easier for me to graph the function using some well, whole numbers rather than fraction for x. So we have a point at 1, 0, and at 3, -1, and oh, I drew 1, 0. All right, 1, 0. And so this is 1, 0, and 3, -1. And actually, I can't even see here. 3, -1. So that's a 3, -1. And the 9, -2. So is 9, -2 even on here? 4, 5, 6, 7, 8. 9, -2. So 9, -2. And then I can see what is going on here. I still have my vertical asymptote at x equals 0, but this particular graph is actually decreasing and not increasing. So let me go ahead and draw this with a different color so that it doesn't blend in too much. So it looks like this. All right. So again, the domain is going to be 0 to infinity, and the range is negative infinity to infinity. So just sort of the exact opposite of what we talked about for the exponential function, because of course, as I mentioned, these are inverses. Since in this particular case, the b was equal to 4 and b was greater than 1, this is going to be an increasing graph, and then increasing graph. And since here b was a third, so b is less than 1, it's between 0 and 1, then this is going to be a decreasing graph. All right, so try to just sort of keep all of that in mind as well, that sort of the base determines whether this will be increasing or decreasing also. So let's try another one here. So again, if there's any questions, please just let me know. But here is the next one. F of x is equal to log base 2 of x plus 3. So y is log base 2 of x plus 3. So I can rewrite this in exponential form as 2 to the y power is equal to x plus 3. Then subtract the 3 to get 2 to the y power minus 3 is equal to x. All right, so now what I'm going to do then is I am going to realize that this minus 3 is going to just be a shift, right, a shift down 3 units. So I need to graph 2 to the y and then just make sure that it shifted down 3 units. So here we have x is 2 to the y minus 3 and y. So if I pick values for y like 0, 2 to 0 minus 3 is 1 minus 3, negative 2. If I pick 1, I have 2 to the 1 minus 3. 2 minus 3 is negative 1. If I pick 2, I have 2 to the second minus 3. 4 minus 3 is 1. And if I pick 3 even, 2 to 3 minus 3 is 8 minus 3, 5. And I feel like that's enough for me to sort of tell what is going on here, all right? So I'm shifting 2 to the y down 3, just so that you're all aware of what is going on here. So we have negative 2, 0. So negative 2, 0. And then negative 1, 1. And then 1, 2. And 5, 3. So 5, 3. So it looks like this. Now this might seem a little bit weird to shift 2 to the y down 3 because, well, what actually does that even mean? All right, if you look up here, right, if you looked at this in terms of x's and not y's, then this would actually be a shift 3 to the right, to the left. So that means that this asymptote needs to shift 3 to the left. And so now, instead of being at x equals 0, it's at x equals negative 3. All right, so then the domain is going to be negative 3 to infinity, and the range is still, so that was the asymptote, and the range is still negative infinity to infinity. Now remember, this is the x-axis and this is the y-axis, right? But if I drew 2 to the y, and I'll draw 2 to the y for you, just so that you remember what it looked like. All right, so 2 to the y, there would have been a point at 0, well, all right, so 1, 0, and at, all right, so then there would be a point at, oh boy, what is this? Oh yeah, 2, 1, and then at where is it? 3, 8. So 3, 4, 5, 6, 7, 8, 3, 8, and it looks like this. All right, now why is this saying it shifted 3 left and this is saying shift it down 3? Well, this is saying that the graph of 2 to the y is shifted down 3, not 2 to the x. So if I actually turn the paper here, then you can see the shift it down 3 of 2 to the y. All right, so that's why I feel like in this case, it actually was a little bit confusing to think of it in terms of 2 to the y than it was in terms of the logarithms. All right, so keep that in mind that when I say 2 to the y is shifted down 3, I mean shift it down 3 if you're looking at the graph like this. All right, so this is x equals 2 to the y, and this is actually x is equal to 2 to the y minus 3. All right, so hopefully that all made some sort of sense there. So let's try another one here. So we have log of x times 2, or 2 log x. So one thing that I can do is just write this as equal to y. All right. So then I will have, then I'll isolate the log to get log of x is y over 2, and then the base is actually 10. So we have, all right, base is equal to 10. So in other words, in exponential form, this is 10 to the y over 2 power is equal to x. So if I make a table, x is equal to the 10 to the y over 2 power, and we have y here. If I have a 0, all right, so 10 to the 0 over 2 is 10 to 0, which is 1. So if I pick a 1, I have 10 to the 1/2 power, and that's really the square root of 10. So I probably don't want to deal with that. But if I have 2, 10 to the 2 over 2, that's 10 to the first power, which is 10. So those are the points I might try to graph here. So I have 1, 0, so 1, 0, and I have 10, 2, so 2, 3, 4, 5, 6, 7, 8, 9, 10, 2, and then the graph just looks like this. All right, so just like this. So this was my 1, 0, and this was my 10, 2. And then I still have a vertical asymptote at x equals 0, and my domain is going to be all real numbers greater than 0, so 0 to infinity, and my range will be all real numbers, so negative infinity to infinity. All right, so now here is another example here. So here we have log base 5 of negative x, if that will be equal to some value of y. Then another way to write this is 5 to the y is equal to negative x. I'll multiply by negative 1 to get negative 5 to the y is equal to x. So then here we go, x is negative 5 to the y, and then I have to pick values for y. So again, if you need that other page, just let me know. But if I pick values for y, then I could pick, say, a 0. So x is negative 5 to 0, that's negative 1. If x is, sorry, y is 1, x is negative 5 to the first, so negative 5. And then if y is even 2, you have x is negative 5 to the second power, so negative 25. And you can see that this gets extreme pretty quickly. So there is a point at negative 1, 0. So negative 1, 0, and at negative 5, 1. So negative 5, 1. So negative 1, negative 2, negative 3, negative 4, negative 5, 1. And then the graph sort of, again, it gets extreme pretty quickly, but it just looks like this here. All right, so there's still an asymptote at x equals 0, and then the domain is numbers negative infinity up to 0, and the range is all real numbers, negative infinity to infinity. Now, this sort of makes sense that this graph is pointing the other direction, or is a reflection, because that's what this negative here means, is that it's a reflection over the y-axis. So this is a y-axis reflection. All right, of y is log base 5 of x. So log base 5 of x would actually be pointing the other direction. So there would be a point at a 1, 0 and at 5, 1, and it would look like this. All right, so that would be y is log base 5x, and this is y is log base 5 of negative x. All right, so it is easy to hopefully see what that negative sign does there. All right, let's try another one here. So f is 2 plus log base 3 of x. So what do we have here? We have this is equal to y. So I'll subtract the 2. So log base 3 of x is y minus 2. And so in exponential form, that's the same as 3 to the y minus 2 power is equal to x. And so then I can make a table. So x was equal to 3 to the y minus 2. So if I pick values for y, such as 2, I have 3 to the 2 minus 2 is 3 to 0, which is 1. If I pick, say, 3, I have 3 to the 3 minus 2. 3 to the 1 is 3. If I pick 4, 3 to 4 minus 2 is 3 to second, so 9. And then I will graph from here. Now, remember, this plus 2, you should suspect just means that this should be shifted up 2. Now, here though, it's in the minus 2 here is in the exponent, and so that will actually mean that 3 to the y is shifted, right, 2 units to the, all right, now, think about what is going on here, that I want to shift the 3 to y, so the 3 to y is going to be shifted 2 units to the to the to the right. All right, so try to remember this for a minute, that this is what is going on here. So there's a point at 1, 2, 1 and 2, and then 3, 3, so 3, 3, and then 9, 4. So 9, 3, 4, 5, 6, 7, 8, 9, 4. So 9, 4. And then the graph will actually just look like, actually, wait a second, that's not, did I get left and right mixed up? I think I did, but because I said I was going to say left and then I said right, because I think I got left and right mixed up, but that's okay. So just we'll fix it in a minute. All right, so there we go. There is the graph. So that's why I said left and then I changed it to right, but then I realized it should be left, and I'm still directionally challenged. So anyway, here is an asymptote at x equals 0, and then just try to remember what is going on here, that the domain is going to be all real numbers greater than 0, so 0 to infinity, and the range is going to be all real numbers, negative infinity to infinity. Now, this was actually 3 to the y minus 2, but if I wanted 3 to the y, then that would be a point at 1, 0, and then at a 1, 3. All right, so 1, 0. So at 3, 1, 3. There is 1, 3. So 1, Okay, so I said 3, 1. So 3, 1. Sorry, all of these are really, really small to actually uh, to count, actually, believe it or not. Like, this is really hard to see over here. So this is 3 to the y. And then, again, I can do the same trick here. And if I move the paper so that the graphs look like this, you can see that 3 to the y minus 2 power was actually just 3 to the y shifted 2 units to the left. But if I look at it in terms of x's, like 2 plus log base 3 of x, then it's shifted 2 units up. All right, so try to remember that this is what is going on here. All right, please try to remember that this is why sometimes, even though you can change to exponential form, it could get a little bit confusing if you're trying to think about how the graph is shifting from the original graph. All right, let's try another one. So now all the stickers on my keyboard are coming off here. So believe it or not, I have Korean language stickers on my keyboard so that when I need to type anything in Korean, I can, and I actually don't have the Korean. Actually, I stopped the video by accident because I pressed the letter B on the keyboard, which apparently B means stop, and I didn't know that. So anyway, let's find the function of the form y equals log base a of x, whose graph is given here. So here we know that they're given an x and a y value here. So then all I need to do is find a. So we have, here we have -1 is log base a of a half. All right, so then what else do you know here? Then you know that, oh, and by the way, all of these have a point going through, all right, 1, 0, and 1, 0. All right, so just remember that if you remember what I talked about last week, if for the exponential functions, if the functions don't have a point going through 0, 1, then you would need to have two equations. So the same thing would happen here, right? It's really like log, like with another constant, like, I don't know, like it's really like a log b of x. That's why I don't actually like the a, because you really want b to stand for base, right? But then you would have to have two equations like that if you didn't have a point at 1, 0. All right, just try to remember that. All right, so now then I can rewrite this as b to the -1 power is equal to a half in exponential form. So a half is 2 to the -1 power. So that means that b must be 2. So therefore the equation is y is log base 2 of x. So there you go. That is it for that problem right here. So here is another one. We have, let's see, we have a point at 9, 2, so that's xy. So we have y is log base b of x, so 2 is log base 9 of x. So, well, b, sorry, b of 9, log base b of 9. Sorry, the 9 and the b actually almost look the same from over here. So now we have b to the second power is equal to 9, and I know 9 is 3 to the second power, and so therefore b must be 3. So the equation of y is log base 3 of x. All right, so hopefully that all makes sense of how I am writing down the functions here. So now we are going to go through this all again for natural logarithmic functions. So let's go ahead and do an example of those. So again, for the natural logarithmic functions, these are just functions with the base of e. So convert e to the b power equals 9 to logarithmic form. So the base is equal to e, the exponent is equal to b. So we have log base e of the 9 is equal to b, but instead of log base e, I'm just going to write natural log, or ln. So ln of 9 is equal to b. So this isn't in again, it's ln. So ln stands for natural logarithm right here, natural logarithm. So just try to remember that that doesn't mean in, and also try to remember that it's not even like, if you're looking at how this is typed out, it might even look like 1 times n, which it's not, it's ln. So just be very careful with the notation. And also notice that I'm writing it with a lowercase l, so it should be with a lowercase l, but that also means because it should be with a lowercase l, you should be extra careful again of the notation. All right, let's convert log base e of b equals -3 to an equivalent exponential form. So the base is going to be equal to e, and the exponent is going to be equal to -3. So we have e to the -3 is equal to whatever the argument is. So e to the -3 power is equal to b. All right, let's try again. Evaluate the logarithm log base e of e to the 9th. Now, if you remember the properties of logarithms, let me bring one of them back up. It said that, and that was quite a while ago, I know, but it was, oh boy, where was it? Yeah, okay. So, here is one of them, right? You have b, so b log b of x is equal to x. All right, so if you think about this, then um, this should sort of make sense because the base is b and the exponent is log base b of x, right? So if you wanted to rewrite this in a different form, then if this is the base and that's the exponent, then that would be the argument of the logarithm. So this is really just saying log base b of x is equal to log base b of x. So if you can think of this in the same way as that, then this is like equal to some value of x. So I can rewrite this. This is base, and then this is the exponent. And so I have e to the x is equal to e to the 9. And so then x must be equal to 9. Actually, I probably made it worse by putting that property over there, but I really thought that it was a different property that I had said earlier, but I can't find it. So we'll just use this one that we've already had until we get to the next section when there's even more properties of logarithms. So Now let's solve each logarithmic equation for x. So we have to try to remember that we are going to try to isolate the x. So that means start by isolating the logarithm here. So let's add the 3 to each side. So log base e of 2x plus 1 is equal to t plus 3. And then that means that the base is e and the exponent is t plus 3. So e to the t plus 3 power is equal to 2x plus 1. And then even though again I don't know what t is, I'll just solve this like there's no problem here, and I'll subtract the 1. So e to the t plus 3 minus 1 is 2x, and then I'll divide by 2. So e to the t plus 3 minus 1 all over 2 is equal to x. All right, so that's how I would solve this equation for x. All right, next one. Natural log or ln of x is equal to 1.548. So then again, the base is not given, so the base will be e, and the exponent will be 1.548. So e to the 1.548 power is equal to x. And I definitely need a calculator for that one. So e to the power of 1.548 is going to be, x is approximately 4.7020566659. Right? What a time to be alive. All right, so now I hope that you enjoyed that one, but now let's go on to finding the domain of each of the following functions here. So the natural log of x plus 1 over x minus 2. So remember that earlier I said the domain of log base b of x was x greater than 0. So the argument always has to be greater than 0. So the x plus 1 over x minus 2 has to be greater than 0. And then I said from our past times solving these that this has the same solution as x plus 1 times x minus 2 greater than 0. So then I can go ahead and graph this. This has intercepts at x equals -1 and at x equals 2. And then I know that because it's x times x, it's x squared minus 2x plus x minus 2, that the end behavior is an even power, so it looks like this, which means that, well, by the way, I really just need to know that since this is an odd multiplicity, right, to the first power, and that's on odd multiplicity to the first power, that this crosses the axis at -1 and at 2. So the graph looks something like this. And if I want to know where this is greater than 0, here it is, here and here. So therefore, the solution is going to be for the domain, -infinity to -1 and 2 to infinity. All right, so there you go. All right, let's try again. The natural log of 2 minus x squared. So I know that the argument 2 minus x squared has to be greater than 0. So I'll rewrite this as -x squared minus x plus 2 so that it's in descending order. I'll divide by -1 to make this a little bit easier for me. So that means I need to change the sign to less than. So I have x squared plus x minus 2 less than 0. I'll factor to get x plus 2, x minus 1 less than 0. And so then, what do you have? Well, you have zeros at x equals negative 2 and x equals 1. So at x equals negative 2 and x equals 1, there's a 0. This is an even powered function, so the end behavior is opening up like this. And I know this is to the first power, this is to the first power. So the graph crosses the axis at x equals negative 2 and 1. So this looks like, well, uh, it looks like this here. All right, so, okay, so like this. So now I want to know where the graph of this is actually less than, right, less than 0. So right here between negative 2 and 1. So the domain is going to be negative 2 to 1. So why were we doing all of this inequality business earlier in the semester? Because we needed it to find just really the domain of these logarithmic functions here. So that's definitely one application. All right, let's try another example here. So this one is just going to be of graphing a function using its exponential form and determine its domain and range, but this one is a natural logarithmic function. So we have f of x is negative 3 plus natural log of x minus 2. So we have y is negative 3 plus natural log of x minus 2. So again, I'll start by isolating the natural logarithm. So I'll add the 3. Y plus 3 is natural log of x minus 2. Then remember, the base is going to be e, and y plus 3 is the exponent. So I have e to the y plus 3 is equal to x minus 2. Then I can add the 2 to get e to the y plus 3 plus 2 is equal to x. So here, if I have x is equal to e to the y plus 3 plus 2, and I have y, now because e is uh, a a number where it's going to be a little bit more difficult to figure out points that aren't decimals, I'll probably just use a calculator for most of these. But I do know that if, say, y is negative 3, I have e to negative 3 plus 3 plus 2. That's e to 0 plus 2, and e to 0, 1. So 1 plus 2 is 3. So that is an easier point to find. But let's say even y is equal to, say, 0. Then e to 0 plus 3 plus 2, e to 3 plus 2, and there I'm going to try to use my calculator here. So e to the 0 power plus 3 plus 2 is, wow, that's already 22.08553692. So I probably want to pick a number that's a little bit uh, smaller, so that I have an x value that's smaller. So even negative 2 might be better. E to negative 2 plus 3 plus 2. So it's e to the first power plus 2. So e plus 2 is about 4.718281828. All right, so here we go. We have 3, negative 3. So here's 3, negative 3. And about 4.71, negative 2. And so then all I need to do then is just make sure that I shift the asymptote as well. All right, so the asymptote is now at 2, and I'll point out again why that is in a second. But the here is the graph. All right, so the domain is going to be 0 to infinity, and the range is going to be negative infinity to infinity. Now, again, why did I know that the asymptote was going to shift 2 units to the right? Well, here was my shift 2 units right, and here was my shift 3 units down, or 3 units downward. All right, so there is the graph of f of x equals -3 plus the natural log of x minus 2. All right, so that is it for this section here on logarithmic functions.